Maybe it is. Maybe you could say.
I guess most of us are back, so maybe let's kick off this session. So welcome to the second session, the afternoon session for the fourth day of the workshop. Our first speaker is Ameesh Shah. He is a PhD student here at UC Berkeley, advised by Professor Sanjay Sesha. He is also a National Defense Science and Engineering Graduate Fellow. He has interned at Microsoft Research and TRI. And the first time I heard of Ameesh's work was when he was an undergrad. He was looking at synthesizing programs to describe behaviors of rats using differential programming. So his roots in neurosymbolic AI goes all the way back to his early days as an undergrad. Ameesh.
Thank you. There will be no talk about rats in this lecture, so sorry to disappoint if anybody's expecting it. I'll be talking about reinforcement learning today, and I'll be talking about formal methods and formal task specifications and the relationship between the two, which is what I've been looking at with Sanjeet for a little while now. So, I mean, for those of you who don't look at RL all the time, this is the basic loop for reinforcement learning. Reinforcement learning asks this question of how do I learn behaviors that are desirable in the world by interacting with the world, right? So the loop is I have some agent, it could be a robot, or you could be a character in a game. You're gonna observe your environment, act according to that observation, and then receive consequences for taking that action, which will be a new observation of the world and some reward. And your goal as an agent is to maximize that reward and update your policy, your behavior, so that you're maximizing reward as much as you can in your environment. And one key thing about reinforcement learning for anybody here who has used it or who has tried to design reward, or who has tried to use reinforcement learning, especially in real world contexts, is that reward design is really important and really hard. And the success of your agent will come down to how good or how well designed your reward function is. Our reward functions, they should be incentivizing behavior we care about in the world and that we like, but we should also be using them to discourage behavior that we don't want. And in trying to capture all of that in a single reward function, it often becomes a process that's challenging. This is a really classic example from early papers in reinforcement learning and AI, and it's about this boat racing game where the goal is to collect as many points as you can while finishing this loop around the track. So you have this task, which is finish the race, but you also get more points for picking up these green objects. And basically what the policy learns and the reward function that they gave this policy or this boat was get as many points as possible, because you get points for finishing the race. You also get points for collecting these things along the way. And what you see is this weird behavior where it realizes that these bonus things respawn after a few seconds. So it kind of just loops around and collects these points and doesn't actually finish the race. And so you have this sort of undesirable behavior that you didn't plan for just because you use the reward function that is natural, right? It's how you score and how you get placed in the game and this sort of behavior. And so one thing that we are interested in is reward engineering and designing good reward functions. But it's tedious at best. It takes often multiple tries. I think for people who have used reinforcement learning for robotics, especially, you require designing and redesigning your reward functions. And at worst, it's difficult to impossible. If I'm trying to learn behavior in the real world, sometimes I can't afford to redesign my reward function after a few iterations. If my robot breaks because I've misspecified my reward, that's prohibitively bad. And so we want to avoid this sort of behavior. And the key question that we ask is, how do I represent desirable behavior? And now, there's a group of folks here who have a background in formal methods. And the field of formal methods has been asking and answering this question: how do we represent desirable behavior in a number of contexts? And formal methods is this practice of how do we specify something I want and verify or synthesize a system that either does achieve that behavior or doesn't achieve that behavior. And in order to do this verification or synthesis in some cases, it's, this field is, we've developed a number of different forms of representations for desirable properties. And in this purpose of this talk, I'll refer to these as formal task specifications. I use the symbol var5, this symbol phi, or LaTeX var5 for short. And so I'll be using phi when I refer to these formal specifications. For example, what's an automata? So if I have some task that I want to fry an egg and write me an essay, in any order, I can design this very simple automaton that captures that behavior and unambiguously does so. And we'll be looking at formal specifications of this flavor for the purpose of this talk. And so this natural question emerges. I have these formal specifications that I've designed in formal methods. Can I use these as objectives in reinforcement learning contexts? Can I learn behaviors that will abide by these specifications? And the short answer, very short answer, condensing a lot of context, is yes, we can. We can use these, and there's plenty of prior work about it. And I won't get into all of the prior work of how this came about, but I think the more salient question that people are now asking as reinforcement learning becomes more popular, and as we have better systems computationally to learn policies, both in the deep context and otherwise, is when should we use formal specifications as objectives? When is this useful? And how does it differ from what people have done or are doing in the context of reward design, in the context of reinforcement learning? So that's what I'm going to talk about today. In order to talk about this question, it's important for us to first talk a little bit about what would the pros and cons be of using a formal logical specification as your objective in a reinforcement learning context. There are pros and cons. So we'll talk about the pros first. What's good about a formal specification? Well, of course, it's a Boolean notion of satisfaction. So you get this level of precision of, am I accomplishing the task, or do I exhibit the desired behavior that I want? And if I don't, I don't. I get a yes or a no answer. And that precision can be useful in a lot of contexts when I care about doing something specific and I, at all costs, want to make sure I'm doing that thing. Another pro about using formal specifications is that they often come with these precise rules of compositionality. So if I have two specifications in the same logical form, it is often accompanied by this very principled rule of, can I combine these two to come up with a new specification that captures the correct behavior exhibited by both of these things, of course, if there are no contradictions. And the last thing that's nice is that you can capture easily these non-Markovian semantics like temporally ordered tasks that are sometimes harder to encode in the context of a reward function in an MDP. Of course, there are a number of cons, right? We're not all using formal specifications to train our reinforcement learning agents these days. And the kind of foremost, at least in my eyes, con of this is that they are difficult to optimize, right? These specifications were not designed to be learning objectives in deep reinforcement learning. And so there's this gap between, I have a representation of it, but how do I actually turn that into a learnable signal, something that can give feedback for an agent, and I can use to train a policy or learn a policy. Another issue is that, with formal specifications, if I'm searching through the space of specifications, let's say I'm considering many possible ones as my, target for learning, if I want to adjust it somehow or change it, it's not like I have this continuous space where I can kind of do some sort of gradient descent or search through it very efficiently. It's difficult to search through this often, non-continuous, this discrete space of possible specifications and solutions. And that makes things sometimes hard when I'm trying to figure out what is the right form that I want to use to train my agent. What's the right form of this objective? And of course, one thing that maybe a lot of folks know that I know especially is it's hard to construct these things by hand. It's hard to come up with formal specifications, especially for people who don't necessarily maybe have a background in formal logic and are maybe trying to use some precise notion of satisfaction, but it's difficult to do so, is one thing. Is a question? Yes.
You're saying
it's also hard to turn on the mic.
Mm-hmm.
It's difficult to construct by hand, but I agree with that in a non-relative sense, but relative to reward functions, is it harder or easier to construct the correct specification?
Yeah, it's a good question. I think that there's a trade-off always, right? I think that there's often cases where I just care about getting some sense of optimality. And in those cases, maybe I want to, you have this cart pull example. I want to stay alive as much as possible. And, it might be easier to just say I get a point for each time I'm alive or each step that I'm alive, or I have some notion of satisfaction or optimality. Or you might say like the closer I am to zero, the better. I think that it's difficult to just construct by hand in cases where it's not as clear what correct and incorrect behavior is. And again, I think you're right that, on the other hand, for reward functions, it's not as easy if I don't have a sense of optimality and I need to sort of separate between incorrect and correct behavior. I will say and this might be a bad thing too, I'll say for traditional reward functions or Markovian reward functions, it might be easier to just come up with something and then iterate on that, as opposed to having to abide by whatever logical form or use a grammar or something like that. And I think that might be a gap that becomes a problem in some cases. Yes.
A related question that I have is that the challenge of specifying the reward, is it more about the representation? That are we doing it numerically or are we using formal representation for it? Or is it more semantic, more sort of like about the information that we need to capture? Because if you go back to the speedboat example that you talked about, the reason reward hacking happens there is because we are talking about the terminal goal. And we are saying that, well, at the end, I want this to be able to get more points. But in trying to achieve that terminal goal, the sub goals that the RL agent will discover could be of many types, some of which will align with what we want to do, some which will be misaligned. That seems to be independent of the actual representation we use. It's more about the fact that we often know the end goal. We don't know what sub goals would make us reach there in a way that is consistent with our expectation. So do you expect formally capturing these specifications to also help with the more information theoretic aspect of it? Or is it mostly about making it more interpretable, about making it more verifiable?
Yeah, so in some cases it will. I think there's this interplay between, can my representation actually help in designing what I want and what you're saying, right? Represent informative behavior. Sometimes that will help. We're actually going to talk about a situation where that might actually be very useful and the choice of representation does have an impact. In some cases, you're right that it doesn't. And actually, for the purposes of this talk, I will actually talk specifically about when the representation is useful. So how the representation enables us to learn things that would otherwise be hard if we were to not use the representation of formal specs. But in cases where that's not true, it comes down more to how much you care about these things, interpretability, verifiability, which I actually will not be, they're not kind of part of what I'll be talking about today. But it's something certainly that we can continue the discussion with at the end. So yeah, I'm glad that Sismit asked this question because this is going to lead into the rest of the talk. So I'm going to go, the last pro and the last con is not something that's going to be within the scope of what I talk about today. But what I will do is I'll take the first of each and then the second of each pro and con. I will talk about a situation where the pro actually is very useful and how we can mitigate the con to help this become something that actually becomes a benefit, a clear benefit in an RL task. So let's first talk about how a precise notion of satisfaction can be useful in reinforcement learning and how we can mitigate sparsity that comes with formal specifications. So a case where this becomes useful is when we have to disambiguate between correctness of a task and optimality of a task. And I think Sismit asked this great question for the boat racing example, where you have this terminal condition you want to reach, and you have these sub-goals along the way that you want to optimize. But these are different things. And in that boat racing case, it would actually be useful to separate the two and say, you have to finish the race at all costs. Upon your path towards finishing the race, you should try and collect as many of these green bonus items as possible. And in a lot of correctness critical settings, besides boat games, we have this sort of problem set up, right? So I may have a task that I certainly want to accomplish, but I may have some optimality condition alongside that I want to be optimal with respect to while completing that correctness. And so I use this example of a patrolling quadruped. So if I have some kind of rough terrain and I have these 3 stations, A, B, and C, that I want the quadruped to patrol, maybe it's a defense task and we have some sort of safety criticality here. I want to make sure I'm doing that. I don't want the quadruped to go run off or do something it's not doing, but along that path, I don't want it to run into rocks. I don't want it to get scratched or fall and potentially risk its health. So I want it to be, maybe minimizing collisions or minimizing, getting buffed around. And so you have this setup where it has to accomplish the task, but while it's accomplishing the task, I want it to abide by some notion of optimality. And so, I don't want to kind of wave my hands too much. And so I'll just very briefly touch on this, but it is difficult. I'll posit that it's difficult to express both the correctness and optimality conditions in a single expression in many cases. I think a lot of folks in here who maybe work with robots can probably attest to this, where you want it to accomplish some task, but you also have, require it to be stable or smooth or abide by certain things, and combining those things is very difficult. And this is where having a separation between correct and optimality can be very useful. Formal specifications allow us, and by nature are about precise correctness. And then we can use a Markovian reward function, a reward function that's within our MDP, to allow us to define optimality within the space of correct behaviors. So then we can ask this question, which is, I want my policy to be correct, but amongst correct policies, which one of them is the most optimal? Question. Yes.
So the question is about correctness on the trajectory or on the policy?
It's correctness of the, so it's a good question. It's a correctness of the trajectories themselves. I mean, ultimately, we're going to be talking about the deep RL context where it's going to be difficult to verify the policy itself, but you want it to produce satisfying trajectories with the highest possible probability.
Okay, so it is a large probability statement. Like you want not absolute guarantee, but maybe a large fraction.
You're trying to get to probability optimality, right? Because it might be the case that in your world, you can never maybe always satisfy the specification. So you want to do it as much as you possibly can.
All right, thank you.
Yes, good question. So I'm going to just reduce this down to a very simple toy example just for the sake of demonstration. We'll take our quadruped and we'll turn it into a dot in a grid. So let's say I have this task where I want my robot, this little green dot, to patrol the red, green, and yellow regions and avoid the blue region. So that's my task specification. And I have some optimality condition where there's these little purple bonus regions, and I get a reward of +1 for visiting these purple circles. So again, I'm going to reiterate, I have to accomplish my task. I have to be correct. But amongst all the possible correct policies, I want to choose one that is optimal. So the first thing that we'll do is we'll talk about how we specify our specification and our optimality condition in our setting. We'll be using Buki automata, limit deterministic Buki automata to be specific and exact, but I won't be kind of going into those details. Or linear temporal logic. Of course, you can take your linear temporal logic formula and you can convert it into a Buki automata that captures the semantics of your LTL formula. We'll be using those automata. And of course, in the Buki automata, your satisfaction condition will be visit your accepting states infinitely often. So you want to produce trajectories that will continually visit this accepting state. In our optimality condition, we're just going to use a standard Markovian reward. We'll attach it to the MDP. So we'll use our standard definition of MDP reward. In this setting, if you transition to a state that is in a purple region, you get a reward of +1. Otherwise, you don't get any reward. So we have our correctness condition, our optimality condition. And the first question I'm going to ask is, how do I combine these things in a way that is readily optimized by deep RL? Right? So I have a deep RL agent. I want there to be a form that a deep RL agent can readily optimize that captures both of these things. And so I'm just going to take us step by step through this process, and then we'll talk about how this actually looks when we put it in practice. So the first thing I'll do is I will take my task specification, and I'll have to compile it down to a proxy reward function that approximates the satisfaction of my original specification. So what I mean by that is that, unfortunately, as I mentioned earlier in the talk, these Buki automata or a lot of these temporal logic specifications, they weren't designed for optimization in an RL context. So we have to come up with an approximate version of that in the form of a proxy reward function. And what we'll do is we'll keep track of where we are in our Buki automaton during a rollout of an episode of reinforcement learning, during a trajectory rollout. And if I visit the accepting state, I'm going to get a reward of 1. And if I'm not visiting an accepting state, I will get a reward of 0. So I want to maximize reward. And by that, I mean I want to maximize visiting the accepting state as many times as possible. And since, as we recall, our acceptance condition is infinitely visiting this accepting state, there's theory in prior work that shows that a policy that maximizes this reward will be closely approximately optimal with respect to the original LTL satisfaction condition. There are some details here that I'm eliding specifically due to discount factors and things like that are important, but not kind of within scope of this talk that I'm happy to discuss. But in case somebody that jumped into someone's head, I just wanted to be clear about the details there. But this is what we'll be using then as our proxy reward. And what we can then do, and so this is sort of one thing that we showed in the work that I'm discussing, is how do I combine these things? And the answer is actually pretty simple. What I can do is I can take that proxy reward function I developed, I'll call this R sub LTL, and I can just combine it, I can add it to the original reward, the optimality reward, the MDP reward. And if I multiply it by some Lagrange multiplier, and if I have that value be sufficiently large, we show that a policy that optimizes this combined reward will actually achieve our original goal, which is it will satisfy the specification with the maximum probability and achieve the optimal reward. I'll briefly go over the intuition about this, which I'm not going to cover much for the rest of this talk, but I'm happy to discuss it offline. The intuition is I care about getting the highest possible value of this reward function. So in order to be probability optimal, I must maximize this. So if this multiplier lambda is high enough, that means that any way I can bump this up, I will prefer over any amount of additional reward I can get. And once I've reached the maximum here, in order to maximize the overall term, all I need to do is drive this term up, right? So the idea is I care about getting this to be as high as possible, right? My correctness condition. Once this has reached its maximum value, then I care about getting this value to be as high as possible. So then going from first I'm at correct and then optimal. Yes, question.
What if you have two completely different ways of solving a task? So both satisfy your LDL spec, but in completely different ways.
Yes.
That you get stuck in a local minima or maxima if you're doing that, right?
You can, yeah. So this is a theoretical guarantee we're making. So we're not making a pat guarantee that, a reinforcement learning algorithm with this is going to get you to the optimal. The guarantee is a policy that optimizes this reward will achieve the original goal of being correct and optimal. So in practice, right, in deep learning, and I'm actually going to show some examples here. In practice, you may run into local optima. This is a possibility, and so you have to, use some tricks to get around that. But does that answer your question? There's a gap between. I'm not making a guarantee on pack learning. I'm instead making a soundness guarantee on the reward formulation that we're developing here.
But it sounds to me like I could also just first train it to do something infinitely often and then say, now I continue training and do some fine tuning. So I don't see typically if you have a Lagrange multiplier, you try to iterate between min max.
Yeah, so again, this is, we were able to derive a theoretical bound. So I think the issue if I was doing one thing first and then another thing later, is that if I don't have both things in my reward formulation that I'm aware of at the same time, I could go from a policy that's correct to a policy that's incorrect because I'm suddenly only caring about optimality and I no longer care about correctness. So you do need to have both things, both terms in your reward formulation at all times when you're training. Yeah.
So I have a question about this psi-induced reward. This reward, if I understand correctly, requires additional states that's not visible to the original MDP and agent, right?
Yes.
So from the agent's perspective, it's suddenly in a POM-DP situation.
So it's not a POM-DP because, so let's talk about what additional, so this is a detail that I am eliding a bit, but you have to couple these states of your Berkeley automaton with the states of your MDP. But it doesn't become a POM-DP because I know the structure of this.
No, who's you, right? Are you the
RL agent knows? So the RL agent knows it has perfect information of what state in this automaton.
So you actually give this additional state to the agent.
You do, yes.
Okay, I see. But during deploy time, is the agent working in the reduced original MDP now?
It's still working in the so the thing about this is now, of course, you have to assume that your labeling function is perfect, that you can transition perfectly from one state to another. But if you do have that assumption, then even during deployment time, okay, I'm in state one of my task of my Berkeley automaton. I saw this label, now I'm in this state, and so on and so forth. So you're not suddenly in some underinformed state, that.
So your whole system, your whole MDP is actually lifted up to
yes, exactly.
State space. Okay, thanks.
Thank you. Cool. So we have this combined thing, and we're going to optimize this. So now the last step would be I'm just going to learn a policy that optimizes the combined reward above. And let's just use our favorite RL algorithm for this, or favorite deep RL algorithm. Let's use PPO and optimize this, right? I have a reward formulation, don't need to do anything special otherwise, and it should be great, and we should profit, and this should work out. So now let's ask this question, does this work? And if it doesn't work, what should we do about it? So let's go back to this example that we were discussing earlier. I'm going to train a policy on this combined reward, and we're going to see what happens in this example. And maybe to very few people's surprise, it's bad. And what ends up happening is it just kind of goes and hops around. It's a stochastic world in a bit of a way, and so it just hops around these purple regions, and it completely ignores the task that it's supposed to be accomplishing. And the reason for this is a very RL-centric reason, and it's because of the reward sparsity of this proxy reward that we were discussing. Again, it only gets a reward once it visits an accepting state. And what that means in the context of deep RL is that through pure sheer exploration, it needs to make this loop and avoid this blue region by kind of random exploration, and then it'll finally get some feedback saying, hey, that was a good thing you did. And otherwise it will get no feedback. And it's very easy to see that if your feedback is that sparse, but your optimality condition is dense, right? I just get a reward every time I hop into these settings, then it's easy for this to get distracted, so to speak, and focus purely on the optimality condition and ignore the correctness condition, which is really bad, right? We really, really don't want this. And so now we have to think about, okay, in deep RL as practitioners, how do we help fix this problem? So the question then, and a question that I'm sure lots of folks in RL ask in general is, can we shape our reward? Can we make our reward more dense and avoid this sparsity issue? And we'll recall, we have this structure, right? I'm glad we had these questions. We know the structure of our Buki automaton. Can we use that somehow to densify the reward? So currently, when I visit this accepting state, that's the only time I'm getting reward. So the key insight here is that I have to, in order to infinitely visit an accepting state in my Buki automaton, I have to, first take some path to the accepting state, and then traverse this infinite accepting cycle in the Buki automaton in order to, infinitely visit the accepting state in order to get the optimal reward. And so the insight that we had here in this work was, why not reward progress along accepting cycles rather than just give this sparse reward for visiting an accepting state? So now, I have this accepting cycle of I visit the red region first, then the green, then the yellow, and then I just transition back to my original state. So why not every time I progress along that cycle, every time I visit one of the next colored regions, why not give reward there, right? And so this is the key insight behind what we're doing. Now, of course, there are kind of pitfalls you have to avoid because there are multiple accepting cycles in your Buki automaton, so you can't just naively optimize all of them. The other thing is that not all of these accepting cycles are achievable, right? So in one of them, between 1 and 0, you take that transition if you're in the red, green, and yellow regions all at the same time. Of course, that's not possible in this MDP. We know that from looking at it. An RL agent who doesn't have knowledge of the dynamics does not know that. So you can't just pick a cycle arbitrarily. You have to dynamically know what cycle is giving you the most reward at any given trajectory and use that to shape reward. So we call this cycle experience replay because we take a lot of inspiration from counterfactual experience replay, which is a kind of a popular technique in reinforcement learning reward shaping. So what we do is the following. I'll just briefly go over it in English, and then we'll talk about an example. So what we're going to do is we're going to act in the world. We're going to collect a trajectory. After I've collected that trajectory, I'm going to look back on that and say, okay, if I were to reason over all the possible accepting cycles in my automaton under that trajectory, which one would give me the most reward? Once I've picked the right cycle that's giving me the most reward, I will retroactively update the rewards in that trajectory. I'm going to go back and backfill them based on the accepting cycle that gave me the most reward. One thing I'll just make a note of, there are a ton of details because we make a guarantee on the correctness of this shaping. And there are a number of details that are kind of required to get that guarantee that I'm not going into in the context of this talk, but I'm happy to discuss. But one neat thing about our reward shaping technique is that you can use quantitative semantics. So you don't just, it doesn't just have to be 1s and 0s. You can kind of reward progress you make towards taking transitions in a cycle, as opposed to just taking those transitions themselves. And that helps make reward much denser, which is really valuable. Yes, question.
So, traditionally when someone is, shaping a reward, the prior literature, the classic literature at this point would tell you about using a potential function on your Markov decision process and, trying to reshape the reward in that space.
Yeah.
Do you know if this is related in any ways to like how that potential shaping would have happened on that on the augmented MDP?
Yeah, so we didn't do a theoretical kind of like deep dive on it, but there is a relationship between the correctness of the, like there's certain rules that you have with shaping using potential function-based reward shaping. The cycler-based reward shaping does abide by those rules. And so you can see it as a way of like, it will still get you the same theoretical guarantees that potential-based reward shaping gets you because it does follow the right rules. We didn't go any further than that, but that's, you know, there's one relationship there. This question, yeah.
The more reward you give for progress that you make towards your optimality criterion, the higher the lambda needs to get, right? Because you're now.
So you the choice of lambda does depend on whether or not you're so like lambda, you know, these are kind of two, in a way, two separate kind of contributions, but you know, you do have to, your choice of lambda doesn't actually depend on whether or not you're using the cycler-based reward shaping or whether you're not.
The more reward I can get on.
So you normalize the reward.
Can you go back to the previous?
Yeah.
Where you had the. Yeah, even further.
So you do normalize reward. So I wanted to show you this example because you're normalizing the reward. So even in the unshaped case, the maximum reward you can get from this proxy is actually the same as the maximum reward you can get from the cycler reward shaping. So that's why your lambda doesn't have to change. So here's an I just want to show this example. So I have this partial trajectory here, just have this partial trajectory. You're going to look at all my possible accepting cycles or accepting paths in my automaton. And I'm going to say, okay, of all of them, which one did I take the most transitions in out of the total number of transitions? So here I took 2 of the 3 to get to the accepting state. In this one, I only took 1 of the 2, and then here I didn't take any of them. So you're going to use this cycle or this path to shape the reward, and that's going to get you a denser reward. Question?
So if you go back to the example that you started with, the boat racing example.
Oh, sure, yeah.
It had figured out that there was a way to hack the reward and be able to collect those 3 green objects and do it repeatedly. Wouldn't the strategy that you just presented, where you're trying to look at the progress towards the overall goal and discover those cycles which will give you the most reward, end up discovering the same hacked behavior?
So it depends on how you frame it. You know, so in that case, those bonus like points, I think would, at least for me, naturally that'll become your optimality condition. The progress has to be like waypoint. And so I think actually what you're asking is a good question, which is, can you maybe not just repeatedly take transitions in your Berkeley automaton and then hack reward that way? It's a great question. It's something that we found. And in order to avoid that, you can only give reward on the first time you take a transition in a cycle. So let's say, for example, there happened to be this, you know, some back transition here, and I just kept taking this transition R here. You know, so I could, in theory, just get reward every single time I take that. But the rule of our cycler algorithm is that you only get reward for the first time you take the transition in an accepting cycle. So subsequent times you take it, you will not get reward for it, only on that first time. And that's important because that's exactly how we avoid reward hacking and maintain the guarantee that this is right and this will work. It's a good question. Yes.
So that's very interesting because now you have a second level super state.
Yeah. So now, so this is, it becomes a situation where in theory, you can actually not provide that, like the soundness guarantee that we make, which is a policy that optimizes this reward is correct, still stands whether we give this additional information to the agent or not. Yeah. Now, giving that additional information is useful because you're telling the agent, this is why you're not getting more reward for, say, taking the same transition. In some cases, that's necessary. We found in some cases that it's not. But you're right that for the policy to have the perfect amount of information and for it not to become a POM-DP, you do need to provide that additional level. That's right.
But I want to ask the level, one level down, like the question of all the purple sort of bonus points that you know, that the agent can collect. But I want to ask that with respect to the discounting factor gamma, because I feel like you must have something that says lambda itself has to be higher than essentially that 1/1 minus.
That's exactly right.
On the purple. Is that correct?
That's right.
All right. Thanks.
Yes. Yeah. We have the full kind of proof worked out in the paper, but that's a part of it for sure. Yeah. So that's right. Okay. How am I doing on time? Not super great, but I will just quickly show the results. So we showed it in a couple of Mujoko environments where we have continuous state action spaces and safety gym, which is kind of a standard benchmark for a lot of these types of papers. What we show is that using our reward shaping, when you both have to balance correctness and optimality, makes a really big difference. if you can see, most of these other baselines that we use, which are other reward shaping techniques, can't even accomplish the original correctness task. And when they can accomplish the correctness task, they either don't do it as much as we do, and they don't get as good of an optimality reward as we do. And so it's important to use reward shaping here, very important. One thing that we also showed is, I mentioned to Sebastian that the contributions of this paper are somewhat disjoint. And as another evidence of that, one of our baselines in blue, which you can't really see here, this should be blue. We actually don't use the optimality condition at all, and we just train it on just the correctness. And even then, it can't. Even when it can't possibly get distracted, it still has trouble learning correctness just due to sparsity. So maybe not a super surprising takeaway, but still something that's important in the context of specification learning. Cool. So we talked about the pros and cons, and we talked about the first one. So we somewhat mitigated sparsity, and we showed that precision is useful. One more thing that I want to talk about with the time I have left is where compositionality can be useful, and how we can search through many possible correct specifications to find the right one that fits our setting. And the space where this is really useful is actually in multi-agent RL. And so one thing I wanted to talk about is, this phenomenon has taken a lot of different terms, like credit assignment, the lazy agent problem. I call it the group project problem. And I think it might be something that a lot of people have shared experience on in this room. So let's say I have a team of agents that want to cooperate to accomplish some task, right? So I have a shared reward. I have these 3 agents, blue, green, and orange, and they want to accomplish a task. Let's say one agent does all the work. So maybe you're the agent who's doing all the work. The problem is, even if you do all the work, if you get all the work done, everyone is going to get the same reward. So if you were in school, in high school or grade school, and you carried the team to a good grade, everyone's getting the same grade. And as a result, the agents who did nothing are going to actually be incentivized to do nothing, to continue to do nothing, because they got reward for what they did, which is nothing. And it becomes kind of this bad loop where then in the next episode of multi-agent RL, those agents are just going to sit there, and fold their arms. And the agent who did all the work, if that agent stops doing all the work, they're not going to get reward anymore. And so you're sort of reinforcing and incentivizing this bad behavior, which is a huge issue, and is something that's pretty common in multi-agent RL. Now, formal specifications can actually be very, very useful here because of their symbolic task structure and because of their notion of compositionality. So let's talk about this now it's kind of a mess, but let's say I have this automaton that I want to accomplish. Just one detail that I no longer care about infinite acceptance. I just want to end up at my accepting state, represented by concentric circles here. So this is a DFA now. And I'm going to represent my task symbolically instead of having some black box shared reward. What can I do now with this? So now I have this team of agents. I have this shared task. What I can do is I can decompose the task and assign agents their individual subtasks. So what this task represents is you have to do A, B, and C in any order. So I can maybe just assign each of these agents these individual subtasks. And now I can design my reward structure so the agents only will get reward for accomplishing their individual subtasks. So now the rewards are separated. All these agents are going to get separate rewards for accomplishing their subtasks. And now my team, every member of my team is incentivized to do something useful. If the blue agent does the task B, but the orange and green agents don't do their tasks, they're not going to get reward. They're not sharing anymore. We've decomposed this. And this is going to help now create a more efficient overall team strategy. One key here is that there are rules, and this is, prior work has established these conditions where I can take decomposition, I can take, sub specifications, and I can verify that the synchronous composition of those is valid, meaning a trajectory that accomplishes the synchronous composition of these subtasks will accomplish the overall task. So I can verify, I can check that a generated decomposition is valid. And there's work that is actually able to enumerate these valid decompositions, right? So it's great, so cool, right? I can take a task and I can break it down into subtasks, and we're all well and good. But of course, there's a clear issue here, which is there are many possible valid decompositions, right? So even though I have a valid one, it doesn't guarantee that that's going to be the best way of breaking my task down. Different agents have different skills. They might be put in different positions initially in their world. and that's going to influence what they can and cannot do effectively or efficiently, right? So even in this simple example, the agents, you could assign the blue agent A, B, or C, and so on and so forth. Maybe the blue agent's really good at task C. Maybe the green agent is in a position where it can't even possibly accomplish task A. And we have to be able to find which of these decompositions is the right one to assign our agents. So this is what I worked on with my collaborators in a separate work, which is how do we find the right decomposition to choose amongst many possible ones. And the procedure itself is relatively straightforward. So I just want to quickly go over what the problem is here. So again, we have our symbolic task decompositions. If we break them down, we can get subtasks with the guarantee that accomplishing them will accomplish the overall task. This will help us make more efficient, overall team behaviors. And of course, the problem is that since many valid decompositions exist, we don't know which one solves the task most efficiently because we, or not when I say we, the agents in our multi-agent learning problem don't have a priori knowledge of the environment, right? This is the standard assumption in reinforcement learning. Question?
So what kind of composition are we talking about? I mean,
the composition is of these diaphases that we take it's the synchronous product of the three, and that's the composition rule.
I see.
Yeah.
So I mean, each component task could have multiple steps, right?
That's right.
And you want to take a synchronous product of them.
That's right.
Okay.
Mm-hmm.
I mean, does interleaving make sense?
What do you mean by that?
I mean, some agent takes one step and then the next agent takes another step.
Yeah, so I mean, since we're talking about synchronous products, there does need to be some level of like coordination, right? Like if there's a shared task between multiple subtasks, then they need to communicate on that task in order for them both to transition, right? Following the rules of synchronous composition. So it's a good question. So in order to find the right decomposition, what we can do is do this on the fly during our multi-agent learning loop. So the process will go as follows. I will have some set of possible decompositions, so some set of candidate, breakdowns of my task. I'm going to pick one, and then I'm going to assign that decomposition to my agents in my multi-agent learning game or my multi-agent learning setting. Those agents are going to try and accomplish the task that I assigned to them. And based on whether or not they accomplished it, they will get some feedback and they'll update their policies accordingly. And then I will get, as the overall manager of this process, I will get some estimate of whether or not those agents were good at the subtasks I assigned them. And I will use that to update the selection method of, okay, which decomposition should I pick next? And now I have to balance trying new decompositions for the agents and exploiting the decompositions that I know these agents are good at or that this team is good at. So in order to do that, we follow a pretty straightforward three-step process. Our algorithm is called learning optimal task decompositions, or LOTAD for short. It's a simple three-step process. So our first step is that we're going to generate a set of candidate decompositions to consider in our task. The next thing we'll do is we'll use a task condition policy to accelerate learning across the different candidates. And then we'll use a multi-arm bandit strategy. So we'll use the UCB algorithm to balance exploring and exploiting different candidates. So I just want to go back and show kind of each of these processes. So, before we start this process, I'm going to generate many possible decompositions. So that's step one. And then step three, which is the UCB algorithm, is going to pick one. And so at the very beginning, it'll just randomly select a decomposition. And then these agents are going to be conditioned on all the possible different tasks that they might be seeing. So they're going to know, okay, I'm in task, I'm in decomposition number 4, and I've been assigned task 2. And it'll try to accomplish that by learning a task condition policy. Based on that information, it'll say, okay, in in decomposition 4, the agents managed to accomplish their task, 75% of the time. And I'll get an estimation of how good that decomposition was. So I'll know, okay, given this decomposition, my team of agents were able to accomplish it, really efficiently, or they weren't able to accomplish it efficiently. That's going to be the value estimates I use in the UCB algorithm. And that's how I'll be able to balance exploring and exploiting new candidates, is by saying, okay, historically, how good were the agents at accomplishing the task? How many times have I assigned that decomposition? and I'm going to balance that, and eventually I'll converge on a solution that I've sampled many times and that achieves a very good shared reward. Yes.
Just a quick clarifying question. Am I to think of this loop as you like restart the MDP every single time where like you're going to completely throw away the policy, or do you have a way to condition on the policy like based off of the new decomposition from an existing policy?
So the policy is conditioned on what decomposition it's currently seeing. So you're not throwing away like the policy at the beginning of any of a new episode.
So how do you tell it about the new updated decomposition? Like how does that get sent?
Like how do we encode that?
Yeah, how do you encode?
We just use one hot encodings of like you have some number of possible decompositions, and
I see. Okay.
Yeah.
I think I have a related question. So I was thinking your decompositions are like multi-arm bandits, are like the arms, but it does sound like it's not that.
So each decomposition is an arm that you can pull.
Except that the agents remember their previous learned policies.
They do.
So the sequence of arm pulls now affect the reward.
That's exactly right. Yes.
So that's not a bandit anymore.
It's not purely a single, yes. So there's context, there's history in the sequence. So we use multi-arm bandits as the inspiration here, but you're right that it can't perfectly be reduced to a multi-arm bandit. Yes, no, we don't, I'm not to claim that we get the guarantees of multi-arm bandits in the setting whatsoever. It's mostly just used as a strategy of balancing, exploring, and exploiting different candidates that we use to decompose. Yeah, right. But it's a good question, good clarification. Yes, not a multi-arm bandits problem.
Yeah, but the top level thing, really now you have states, right? So
yes, you do.
You are going back to a meta RL type of setting.
You are.
Yeah.
Yes, okay. Yes. And so here, I mean, for the purposes of our experiments, it just comes down to more of a heuristics of how do you balance making sure that when you explore candidates early on, your policies have not learned as much, right? So they're going to be worse inherently at accomplishing the task just because they haven't seen it. So you have to balance exploration. You have to be very careful early on to make sure you're not too quickly converging on a solution. And that just comes down, at least in this work, it just came down to carefully balancing your exploration. But it's a good question. I'm probably almost out of time. So I just want to quickly go through our experiments. We beat all of the baselines that don't do this sort of informed search or don't break down the task at all in general. On a number of things, including Overcooked, which is a super popular multi-agent benchmark. And just to close, I just wanted to quickly kind of summarize everything we've talked about. Formal specifications are useful. When should you use them? We talked about two settings, and I think that to be more broad about it, if you have a precise satisfaction condition you care about, using a formal task specification can be very useful in RL. If you care about compositionality or decompositionality, it can be very useful. So I know Bayezid 2 days ago talked about how compositionality can be helpful in a multitask setting. We talked about a multi-agent setting today. And one thing that we're looking at now is exploring formal structure in foundation models. So we've left RL, but we're still interested in seeing how using this sort of symbolic structure can be useful in that context. So thanks to my collaborators, and thank y'all.
Thank you, Ameesh. Are there any questions?
Thanks for the great talk. I was wondering on the last part of your talk, do you somehow capture the interactions between the agents that are relevant when you're saying I'm decomposing my problem into separate subproblems,
yes,
but they're interacting, right? And
it's a good, yeah. So this is a great question. It's something that I didn't include that we do address to an extent in the talk. There are certain interactions between agents that are required but are not encoded within the subtasks. And in order for the agents to learn behavior that actually includes that correct kind of cooperation or that correct interaction, we do have to make the agents aware of both their subtasks and the overall task and reward completion of both, so that they're not only interested in accomplishing their subtasks, but that they're interested in taking actions that help aid other agents into accomplishing the overall task at hand.
There's very old work on coordination graphs. Does that ring a bell? Is that connected?
No, we haven't looked at that.
Okay.
I think that, yeah, I'm not sure whether that's encoding the explicit actions of the agents or whether that's encoding the task structure. Here, of course, we're only, the policies that get learned are, not with, those are learned, right? And those are represented as neural networks, but we use the structure for the task specification and decomposition.
I'm curious about what types of decompositions were actually learned. So, DFAs are closed under negation and disjunction. And so oftentimes I might be able to like rewrite these as assumed guarantee kind of properties.
Yeah.
And so I'm curious if you typically found decompositions that look just like chains or, kind of sequential reach avoid, or if it's, there was more interesting structure to it.
Yeah. So we covered a few different types or our task structures had different levels of complexity. Some were just chains and then ended up being just like you assigned different chains of tasks to agents. There were cases where you needed different agents to be in different parts of the MDP at a certain point at the same time for these transitions to occur. And so there was a little bit of reach avoid, but I think from what I recall, I don't think it got any more complicated than sequential reach avoid for most of these decompositions.
Yeah. Okay. Thanks.
You're 10 minutes over time, so we can stop here. Let's thank the speaker again. We reassemble in 25 minutes, 3:15.